Going back to today's tutorials, today will be centered in how to control a one-phase voltage source inverter. We have selected that in order to show how the capabilities of a smart control are not limited to several topologies or are not limited in any way. We have selected this option as we do not want to, let's say, cover a power electronic course, but show how a smart control can easily perform this task. So what we'll be doing today? We will be defining all the transfer function of a BSI inverter, the plant, the sensor, compensator, etc. And Smart Control will provide to us the parameters of the compensators. We will be controlling the inverter with two nested loop, an inner current loop and an outer voltage loop. So we will start, as we said here, with a paper set with the mathematical modeling of the converter. Once we know the transfer function, we will go to a SmartCtrl Equation Editor, and the coefficient of the compensator will be sent to a template we have in PSIM to analyze the control that we have created. So to start with that, I will open a tutorial number 11, which is mainly what we will be covering today. So this tutorial is based into the mathematical analysis of this converter, this BSI converter. So you can see in here a block design of this converter. We have an input DC voltage, a switching matrix, typical for switch bridge, and a filter, an LC filter, and a load. We will be sensing the current. We will have an inner current loop with its compensator. That loop will actuate over the modulator, which will be switching the MOSFET. And then we will have an output voltage loop defined, or whose reference will be the power that the result against the measurement and the reference will be inserted in a compensator, whose output will be the reference of the current loop. So a smart control can work in several ways. For example, there are already created templates of a lot of converters. However, today we want to show you how to work with a smart control with a converter that is not covered by those templates. So in this case, we are supposing that the user has already done all the mathematical modeling of the converter. In this case, all these mathematical expressions are covered in the document, so we will not cover today in very much detail. Anybody interested can download or access the tutorial and check that. In here, we have the specification. So we will have a total power of 5 kilowatts. DC input will be 400 volts. Output, the sinusoidal output will have an amplitude of 230 volts and a frequency of 50 hertz. LC filter will have 200 microamps and 33 microfarads with its parasitic elements. We will suppose that we want to model also the sensor, which sometimes they are not models, and when control is really implemented, several problems arise. So we will be consider them from the very beginning. So they will be again, in this case, for example, 0.02, and in this case 0.25, and a bandwidth 3 kilohertz in both cases. So now it comes to the mathematical modeling. Mathematical modeling is performed twice. for the inner current loop and also for the outer voltage loop. In both of the cases, a feed-forward technique is applied. Feed-forward technique is based into adding, let's say, an additional transfer function in order to neutralize several elements in our control diagram that we want to remove. And we want to remove so the equivalent plant is make more, let's say, is make simple, more easy. We can see in here, in the case of the current loop, how the diagram, the control diagram is this one. So this is the control loop. We have the compensator. We have the sensor transfer function. As you can see in here, it's just a gain and a bandwidth. And we have our current plant. As you can see, there is a block in here, 1 divided by SL plus the parasitic resistor. This is the typical transfer function, but there is another nasty terms in here that we are going to try to remove. What we will introduce to remove these ugly terms is the feed-forward. So the feed-forward will be something that multiplied by all this term will provide a unitary gain. In this case, all the mathematical modeling is done. So we have achieved a transfer function which neutralize all these terms. So our block diagram becomes this reduces thing: the compensator, the sensor, and a reduces plant. So now we have determined the transfer function of our inner current loop. So we are going to open a SmartCtrl. So I open a SmartCtrl. This is all the new features introduces in this version. So we close that. And here we see the window we have seen in a few minutes. We have seen back a few minutes ago. We will go to Equation Editor. And in here, as you can see, it automatically asks us for the plant transfer function. So we now open the editor. We go to the files that we provide, in this case here. This is all the code that we will be using today. Tutorial provides this code, and also this can be found at the very end part of the tutorial document. So we copy it. I copy, I paste, and let's check that. As you can see in here, it starts with the definition of several parameters, the very same that we have specified in the document: the total power, output voltage, switching frequency, modulating technique, modulating parameters, output filter values, the definition of the current sensor, the voltage sensor, etc. We also have in here the transfer function of a low pass filter. You can see it here. It affects the gain and the bandwidth. And in here, we start with the current loop. Current loop, we define it as 1 divided by Ls plus the parasitic resistance. So this result is 1 divided by zeta L, which is Ls plus the parasitic resistance. So the transfer function we need to send back now is this one. So we go down here and return it. Press OK, press compile, and in here you can see it is already plotted, and we need to define the switching frequency. So by default it is 100 kilohertz, and our transfer function is 10 kilohertz. In here we can actually export this transfer function, so we can use in a third-party software, etc. And also we can import transfer function from external resources. The functioning is the very same. We just click, it asks where it is the transfer function when we want to export or to import. We just select that, press OK, and it will open in the very same graph. So we have defined the plant, and now it's time to define the sensor. So by clicking OK, it now asks for the sensor. We will apply the very same technique. I paste the code, click on Editor, and previously we see that the current sensor is defined here. So the transfer function that we need to return now is his GCS. So I will return now GCS. So just OK, compile, and now SmartCtrl doesn't ask us for any switching frequency because it is the very same. There is no need to ask it all the times. Here we have the plotted transfer function of the sensor. As you can see, it's just a low pass filter. So we just click OK. And now we have defined the plant and the sensor. It's now time to define the compensator. There is a list in here where we can choose the option that we prefer. We have type 2, type 3, PI analog, and PI. PI is the typical control PI. I mean the one that we find in control or controlling textbooks. PI is the analog implementation of that PI. Equation means that we can introduce whatever compensator transfer function that we need. For example, if we have several sampling issues because we are sampling at a quite lower frequency and we need a higher bandwidth at the controlling loop, we can introduce in here a P-resonant compensator, etc. It is introduced in the very same way that we have introduced the transfer function for the plant and the sensor. So we just click here. Always there is an example. For example, with set default, a PI compensator transfer function is given as an example. But today we will, sorry, I destroyed that. So I will redo that quickly, compile, okay. The sensor will return the sensor transfer function, compile, okay. Yes, sorry for that. Today we will be using the PI analog compensator. However, SmartCtrl also allow us to create a digital compensator just by clicking in here. This list will be updated with all the digital alternatives. So we can select them. I will select the PI analog to be coherent with the document. And in here, we have all the modulation parameters. Those parameters depends on the template that we will be using in PSIM. So I will introduce the same values as in the document. So as you can see in here, we have 2, -2, and half of the period. So 2, -2, and half of the period. This value in here is the rising temp of this waveform. So if that is 50% of the total, so 50 microsecond is the 50% of 100 microsecond, this waveform will be a perfect triangle. It will not be like a saw, just a perfect triangle. So we just click OK. And now we have defined the full loop. So now we need to define the control point that or the control solution that we want to implement. Here it is also defined. So we will select a cross frequency of 2 kilohertz and a phase margin of 45 degrees. So 2K and 45. To select a point in this solution map, we have to take into account all the weight area are stable solutions. Solutions in this area will be slower solutions as the cross frequency is slower. Solution in this part will be a quicker loop. The lower we select the phase margin, the higher oscillation or the less damping that we will have. So we select that point, say OK, and this is the SmartCtrl analysis window. In here, we can select a different point. For example, as you can see in here, that is a much slower point, much slower solution. But as you can see, there is no ringing in that step response. However, if we go to the original point, we have a little bit of overshoot, which is quickly dampened, and we have a quicker loop. So in this case, for our application, that point will be quite useful. So I will point out it back to 2 kilohertz and 45 degrees. In here also we have the additional feature to discretize the control. We have seen previously that we can select analog compensators, or we can choose digital compensators. However, we can also select an analog compensator and then discretize that. This is the option to do that. So we just click on Calculate Digital Compensator. We introduce the sampling frequency, the bit numbers of the ADC converter, and the accumulate delay of our loop. So the phase will be compensated. We just click OK. And as you can see here, another transfer function has been enabled. So we can see in light pink the transfer function of that discretized compensator. We will be using an analog compensator, so we will not be using that. Anyway, its results will be found in here. Those are the coefficient for that compensator, for that discretized compensator. However, as we are using an analog implementation, we just store those values, 93 and 328 microseconds. Those are the coefficients for our current loop compensator. So now it is time for the voltage loop compensator. We have 1 second, please. Yes, we have found our current loop compensator coefficient. So now it's time to go to the voltage loop ones. So the voltage loop can be seen as this diagram. So now the inner current loop is shown as a current source, as a dependent current source, whose reference will be provided by the voltage compensator, and it can be seen as a filter, a capacitance, and a load. So after all the mathematical expressions, we will have a transfer function or a control loop like that, with a compensator, a voltage compensator, a sensor, which actually have the very same equation as the current sensor, just a first order low pass filter. And if we see now the appearance of our plant, we see a term that depends on the capacitor. So 1 divided by the capacitance multiplied by S, and with the parasitic resistance of the capacitor. And also now a coupling ugly term in here. That term, we can remove that again with a feed-forward technique. So we can do that as it is seen in here, introducing a transfer function, in this case a complex transfer function, that multiplied by this ugly term will create a unitary gain. So I think, yes, in here. If we apply the feed forward, our transfer function of the plant will just become 1 divided by SC plus the parasitic resistance of the capacitor. We can apply the feed forward or not. As we have applied the inner feed forward compensator, we will not apply the output loop 1, the outer loop 1. You can apply that if you prefer, and if you see the code, we will be seeing that in a minute with more detail. Both options are provided. We will not apply that in this case because if we introduce the transfer function of that, let's say, variable current source, we can opt to a higher bandwidth in our outer voltage loop. So that will be quite useful today to show exactly how we can increase the performance of our loop with the aim of SmartCtrl. So I will go back to SmartCtrl, open a new project. So open a new equation editor. Now I paste the very same text, and let's see what we will be returning now. The transfer function we have seen is this one, 1 divided by the sorry, by CS plus the capacitor parasitic resistance. And if we apply the feed forward, which is this transfer function in here, we just have to divide that by a constant. That constant is the gain of the inner current sensor. However, we will be, in our example today, introducing the fourth transfer function. That includes the transfer function of the closed loop inner current loop. To do that, we have to introduce the values of the compensator. Those values are the very same that we have calculated before with a SmartCtrl, so about 94 and 330 microseconds. Those are the very same, values that we got previously. You see, almost 94 and about 330 microseconds. So those values are the one that we have collected in here. Here is the transfer function of a typical PI compensator. And this transfer function, GI, is the closed loop transfer function of the current loop. That is a complex term, but it is how the closed loop is seen, how the inner current loop is seen by the outer voltage loop. So this transfer function is multiplied in here by our plant, and this provides the plant transfer function for the voltage outer loop. So this is the function we have to return. We return that, press OK, compile. We have to update our transfer function to 10 kilohertz, which is the one that we will be using in this example. Click OK. And again, SmartCtrl asks us for the sensor equation editor. As you can see, it's exactly the very same procedure that we performed before in the case of the current loop. Now I will paste the code again. And now I will be returning the voltage sensor transfer function, which is GVS, this one. So I uncomment GVS and compile. As you can see, the way of working is quite easy, as in the very same file, we can insert all the transfer function that we need for all the loop that we need, and then return only the transfer function that we need in this moment. In this case, is the sensor equation editor. Sorry, the sensor transfer function. So we just click OK. And again, we have defined the plant, the sensor. So now it's the time for the compensator. Again, I will use the PI analog just to be coherent with the document of the 11 tutorial, but you can use whatever compensator with enough power, that's true, you need. So now there is a difference with our inner current loop. The output of the voltage loop is the input reference of the current loop. So the voltage loop does not contain any modulator. So to overcome this issue, we have to define our modulator with an unitary gain. To do so, we just have to introduce a peak value of 1, a valley value of 0, and a rising time of the total switching period. So that will be 100. By doing this, we are inserting an unitary gain modulator. We just click OK. And now it's time to select the point in solution map. So I don't remember the solution we chose before, but well, you can see in here all the fields that we have been fulfilling, in this case, the modulator. And yes, we select 1 kilohertz and 40 degrees. So 1 kilohertz and 40 degrees. We just click on update, OK, and OK. So this is the analysis window of SmartCtrl, in which we can see the output voltage loop. The very same matters that we talked before apply now. We can discretize that compensator just by clicking in here. We can modify the point and see the effect in real time over the body plots of the plant, which is this green trace, and the open loop transfer function, which is the pink one. We can see the response against a reference step, and we can see the Nyquist diagram. The values were 1K and 40 degrees, so I update them, 1K and 40 degrees. And now the output of SmartCtrl is this, the coefficient for the outer loop voltage loop, yes. So that is 1.64 and 144 microsecond. So now I will go to PSIM to check our template. So I will open PSIM. Yes. I will open the template. So this is the template. It is actually compiled, so we have to unpack it. And in here, we can see the power stage, in which we have the input voltage with its capacitance, the switches, the filtering, the LC filtering, output load. In here, we have the modulator. It's just, well, it's implemented as a subcircuit, but you can see in here that is the typical one-phase modulator. In here, we have the current loop, and in here, sorry, the voltage outer loop. Voltage outer loop has as a reference the power we specified before. It goes into the gain which compensate the sensor gain. Then it goes to the compensator. Well, after some limitation, it goes out as the reference for the current loop. In the current loop, we calculate the error, introduce the compensator. This is all the feed forward that we have implemented, and then its output is the modulating signal that goes in here. And after the modulator, all the switching instant or switching signal are created for those IGBTs. Additionally, we have a couple of steps in order to check the response of this control to perturbation of variation of input voltage. This is a 100 step in the 400 nominal input voltage. And in here, we have a 1/3 output load step. Those steps are commanded by this control in here and by this one. And we also have another 2 items. Those are parameter files. This one contains the very same, let's say, parameters that we have defined for our control. Those are the power, the output sinusoidal specification, the input voltage, switching characteristic, LC filter parameters, the sensor gain and bandwidth, etc. And in here, we have our compensator coefficient. Those are the parameters that SmartCtrl has provided to us. So we have for the current sensor around 94 and around 330 microseconds, those very same. And for the voltage loop, we have around 1.5 and 144 microsecond, those very same coefficient. So now I am going to simulate that. And now we are going to check its response. I will open. I think I can actually do that. 1 second. No, it seems that I cannot. So I will manually load all the waveforms. So we will be first of all looking at our modulator, so VCAR and the modulation signals. So the carrier, modulator number 1, modulator number 2. Now we will be looking for the bridge intermediate voltage via V, output voltage, and the DC one. So via V, output voltage, and the third one was VDC. VDC, this one, yes. Next one is the current and the referent of the inner current loop. So we have the referent current, ELM and EOM, ELM and EOM, yes, and the equivalent for the voltage loop, so VOM and VOM ref. So VO and sorry, it was VOM, yes. So VOM and VO ref. That's it. As I said to you previously, we have an input voltage, which is this green trace step of 100 volts. So it goes from 400 to 500 volts. We can see in here that only the modulating signal is affected, not the carrier or not too much the current, and definitely not the voltage. You can see in here, there is no step in the generated voltage. And we also have another step, which is this one. I think I can use, yes. in here is the first step, and in here is the second step. This step is an output load step. So as you can see, current is increased, modulating signal is updated, but there is no step at all in the output generated voltage. So as a conclusion, the control that we have performed in SmartCtrl is not only fully stable, but is quite capable to respond and in quite a small time and without a, let's say, quick enough so that our output voltage is always perfectly controlled. In SmartCtrl, you can select several different points in the solution map and try impacing with those coefficients, and you will look exactly at you can analyze or do the analysis of how to extract the best performance for your application. In this case, the best performance in this application is this one or around this one. And we have seen how SmartCtrl has facilitated us to arrive that solution. So that is the content of today's tutorial. This is our contact information. In case you have any doubt, you need any assistance, or in case you want to try SmartCtrl or buy it, those are the emails. So